that will wrap it for the week, I think, actually, as Thursday is a holiday. So got a little bit of lecturing, a little exam, then, rest of the week, not have nothing to do, hopefully. All right. So we're in chapter 19. And again, chapter 19, we talked about transition metals last time, or at the beginning of it. Again, just some of the general trends that happen with transition metals. Um, we also talked about things like, again, electron configuration and those types of trends that we see. We also talked about coordination compounds, and remember, a coordination compound is essentially really an ionic compound. So there's sort of a positive part and a negative part, and we have in a coordination compound a complex ion, which can be positive or negative. We also have a counter ion, which also could be positive or negative. So you could kind of think of them almost like ionic compounds, as I mentioned. There's some rules that we talked about in terms of naming them. We usually always have the metal and the complex ion at the end. Usually use the Roman numeral for that. We put the ligands, which are the guys that are attached to it, in alphabetical order without the prefix in terms of determining that. And then we just really named a counter ion like it normally would be named an ionic compound. So, for example, if we had two BRs at the end as our counter ion, we would just call it bromide. If we had, say, two potassiums at the beginning of the coordination compound as our counter ion, we would just call it potassium. So, other weird things in that is, again, if the complex ion part is negative, we go with sort of the older school way of naming, where we put ATE at the end of it. So, iron, for example, is ferrate, plumate, and all those type of sort of names for the metal. We also talked about coordination number and ligands. Remember that there are some that are monodentate, which means for every ligand, it attaches to the metal in one atom. There's ones that are bidentate, which means for every ligand, it can attach basically two atoms per molecule. Um, things like oxalate, we saw that ethylendyl diamine, which is En, also attaches in two places per. There's some that could also do multiple places as well. Those are sometimes referred to as polydentate ligands, something like EVTA, for example. That's that big one that we saw that basically attaches in 6 different locations per molecule. Why that's important to recognize those type of ligands as either being monodentate, bidentate, or polydentate is it affects the coordination number. So the coordination number definition really is the number of atoms that are directly attached to the metal in the complex ion. And those atoms we're talking about come from the ligands. So if you had something like Cl minus, it's going to attach obviously in one place. So for every one of those Cl minuses, you get basically one coordination number. If you have something like oxalate, which will attach through the 2 single bonded oxygens per molecule, for every one of those oxalate molecules, you will get sort of a coordination number of 2. So, so it's important to recognize, these things, those ligands, as either, like I said, polydentate, monodentate, or bidentate. Any questions on any of that stuff that we talked about sort of last time? Okay, we're then going to talk about coordination compounds and isomers. And some of this will be sort of hard to visualize. Sometimes it is isomers in general, very hard to sort of visualize in 3-dimensional space. But basically, an isomer, just in general, is something that has the same molecular formula, but usually some type of different connectivity. So if you go on to organic, you'll talk a lot about isomers, and that's sort of your basic definition of an isomer. Is really you have something that has the same number of elements. So, for example, in organic chemistry, something maybe that has 5 carbons and 10 hydrogens. But you can make a whole bunch of different sort of compounds depending on the way you sort of attach those 5 carbons and sort of 10 hydrogens our 12 hydrogens. And you get these different compounds, which are known as isomers. And because they're kind of attached differently, sort of arranged differently, they typically will have different properties depending on sort of how they are arranged a lot of times. So as you can see here, sort of a flow chart of different types of isomers. There are structural isomers, and structural isomers, they have different bonds. And within that, there's two types of sort of structural isomers. There's one that's known as coordination isomers, and one that's known as linkage isomers. And we're going to talk about each of these in a little bit more detail in just a second. There's also, on the other side, sort of what I refer to as stereoisomers. These have the same bonds, but different sort of three-dimensional arrangements of how they are located, sort of in, again, three-dimensional sort of space. And that creates what are known as geometric isomers, or sometimes referred to as cis or trans. And we have some optical isomers as well. So isomers in general are really, you're kind of dealing with the same alphabet, if you will, the same elements and everything. Again, some different sort of arrangement or connectivity a lot of times is what gives us these different types of compounds that have different sort of properties. So let's start with linkage isomers. I'm sorry, I would start with coordination isomers. I'm sorry. Coordination isomers, here's a couple of examples of it. And if we sort of look at each of these, we can just kind of keep track of everything. There's one chromium, basically 5 NH3s, an SO4, and a Br. And here we got one chromium, 5 NH3s, a Br, and an SO4. So they do contain the exact same numbers of everything going on. But when we look at sort of the arrangement here of what's going on, as we talked about before, usually in our bracket here is our complex ion. And that would make the Br here our counter ion in this case. And again, in terms of sort of oxidation state, that's 0. That's -2 for our sulfate. That's -1 here for our bromide. That means our chromium here is going to be +3 in this particular case. So in our first sort of arrangement here, what we have is the complex ion is really a chromium attached to 5 NH3s. And one sulfate here. Not necessarily drawn correctly in terms of attachment. And on the outside of this complex ion, it has an overall charge of +1, basically. Again, and we get that from adding these together. +3 and -2 gives us a +1. That's why we have only one bromide here acting as a counter ion as Br- here. Again, acting for our counter ion. And the second sort of coordination compound here, again, this is our complex ion part. The sulfate here actually is acting as our counter ion. And in this particular case, if we kind of go through everything, NH3 is 0, Br is -1. Our counter ion is actually -2 on the outside. And that means, again, here we have +3 for our chromium. And the difference here is, in this case, our complex ion is the chromium still attached to our 3 NH3s, our 5 NH3s. And instead of the sulfate being attached, it's actually the bromine in this case. So the bromine is actually part of our complex ion. Overall charge on this complex ion is actually +2. Again, +1 and -1 gives us +2 for our complex ion part. That is why we have one sulfate here with a -2 charge acting as our counter ion there. So here in coordination isomers, what we see is, in the top part, the sulfate's actually part of the complex ion. In the second one, the sulfate is actually the counter ion, and the bromine is actually the part of the complex ion. So again, they have the exact same sort of formula, but obviously different connectivity. The difference is right here. Again, sulfate is attached to complex ion 1, while Br is attached in the other. So again, coordination isomers sort of difference in terms of how it's sort of connected. Any questions on that type of isomer there? Now, another type of isomer is a linkage isomer. And in a linkage isomer, much like the name implies, the difference really lies in the actual linkage of the ligand. So here we're not having necessarily two different ligands coming in, or one is a ligand and one's not a ligand. We're actually using the same ligand. And if we look at NO2 minus, for example, just kind of draw the letters here. In certain cases, it can attach this NO2 minus through the nitrogen, as it's got some lone pairs. While in other cases, the oxygen here can basically attach in. I didn't draw NO2 correctly with all the bonds, but that's sort of the idea of where the attaching is going to be. And that's what we see here in what the attachment for that ligand is actually happening on the nitrogen in that particular case. While if we look at B, the attachment is actually happening through the oxygen here. So the formula here would be exactly the same. Obviously, they both would have NO2 minus as part of it, but the actual difference that we see here is the actual connectivity of the ligand itself. So again, in one case, the nitrogen is connecting. In the other case, it is connecting through the oxygen. Any questions on sort of linkage isomers? So linkage isomer, you have sort of a ligand where it really has multiple connectivity points in the sense that, in certain cases, it could connect like we see here through the oxygen. In other cases, it may actually connect the ligand itself through a nitrogen in this particular case. That then brings us to another class of isomers, and these are sometimes referred to as stereoisomers. And we get, first off, geometric isomers, which are sometimes referred to as cis or trans isomers. And if you take organic chemistry, you'll see a lot about cis and trans. But basically what cis means is sort of same side. And trans means sort of opposite sides. And a lot of times, for example, in organic chemistry, a lot of cis and trans isomers develop when you have sort of a double bond between two carbons. And what we're talking about is you maybe have a group that is on opposite sides of the double bond, and that's sort of a trans, or, you have some groups on the same side of the double bond. That's what is referred to as cis. So in sort of coordination isomers, what we're looking at is our coordination compounds. We're kind of looking at sort of same side or opposite sides, usually of sort of the plane of the molecule. So is it kind of above or below the plane? Do those groups sit, in the same side of the plane in sort of three-dimensional space? So geometric isomers, they have the same atoms and same bonds, but they do end up with sort of different bond angles. They are common in square planar complexes. Square planar complexes, right? Kind of 6 electron pairs and 4 bonds gives you that square planar, the expanded octet sort of geometry that you learned maybe at 50. So here's an example here between these two. We have cis and we have trans isomers here, are PT, NH3, 2Cl. Again, if we just straight up look at the formulas here, they look identical, obviously. But the difference is sort of the arrangement that we have here. So since this is all sort of one plane, if we look at sort of the CLs, for example, they're on sort of the same side of the plane. Also, the NH3s are on the same side of the plane, these two groups that are in common. And that's usually what you look for when you're sort of deciding cis or trans, is you're looking for a couple groups that are in common. So things that are attached that are the same and sort of their locations to each other. And down here, we have the trans version of it. And again, we could kind of see, for example, we just look at the chlorine. we have them on sort of opposite sides of each other on that plane, and that would be what is referred to as trans. That usually gives rise to different sort of colors as well, different sort of properties in these sort of compounds. As you can see, the top one, which is cis, is yellow. The bottom one, which is trans, it's also yellow, but more of a pale yellow color. So it has some different sort of properties. And typically, when we talk about isomers, we typically will sometimes kind of just put that little prefix in front of it and go cis, the rest of it there, or trans, sort of the rest of it. Here's another couple of examples here. The top one is trans. And this is, by the way, that we were looking here at more of a coordination number of probably 4, right? On each of those. Here, we're looking more of a coordination number of 6. And this is more of our octahedral arrangement. So if you remember, 6 electron pairs, 6 bonds, it's an octahedral. And if you kind of think about sort of the chlorines, which are in blue, and we have sort of this plane here that's happening, you have sort of a chlorine above and below the plane, and that is sort of opposite locations, as you can kind of see here, more in a 3-dimensional sort of arrangement. They're opposite sides of sort of the center plane, if you will. And again, that's going to give you that trans location. As opposed to here, we kind of have above and on the plane. So they're both sort of connected in the same sort of part of the plane, and that would give us our cis sort of location. As you can kind of see here, they're both sort of up on toppage, if you will, of that center plane, giving us that cis transformation, or isomer in that case. Now, we also have what are referred to as optical isomers. Optical isomers are isomers that basically have opposite effect on plane polarized light. And what that means is some molecules can sort of rotate light in one direction or another. It gives rise to something referred to as sort of D or L sort of isomers, depending on the angle at which it sort of moves. And it brings up something that's also oftentimes sort of talked about in terms of isomers, and that's molecules that basically have non-superimposable mirror images. Those guys are what are referred to as chiral. So in general, a basic definition of a chiral molecule is something that has 4 different groups attached. So for example, a lot of times that's a carbon with 4 different groups attached to it. That creates something that's known as a chiral carbon and a chiral molecule. And what that basically means is kind of what it sounds like is if you took the molecule and you basically kind of put it up in a mirror, this was the mirror here, and you pulled out that mirror image, you would not be able to superimpose that mirror image perfectly on the original one. So the classic example is if you put your hand up, you get your other hand facing back to you. So if you pull out the mirror image, you can do as much as you want. You can never get them to sit perfect on each other. You can't get the thumbs and thumbs to match, even though I do have thumbs and thumbs matching in this arrangement. I have palm up on one, palm down on the other. They're not perfectly the same. So you could try to rotate your hands. Don't injure yourself before the exam doing that, but you could try to rotate it as much as you like. You'll never be able to get sort of your mirror image, which is your other hand, if you took it out of the mirror, to fit perfectly on top of each other. Palms up, palms down, and thumbs in the right location. You'll never be able to do that. And that means that, that's sort of what is referred to as a chiral molecule, or sort of reflection of our hand. Something where you do have a mirror image that is superimposable, that also is sometimes referred to as being achiral. And those are guys that have basically mirror images that are superimposable. The isomers are sometimes referred to as enantiomers as well. Any questions on that there? So here's just an example of that. Again, we can use plain polarized light that kind of goes through a filter, polarizing and gives us sort of waves heading in both directions. And again, we can oftentimes do that, have a molecule, and we can see how far this angle sort of rotates. And again, that sort of develops us some different types of molecules, especially say with carbohydrates and stuff like that. You get things like D and L. Here's maybe a better picture than my demonstration. Again, if you put your sort of right hand up to the mirror, your mirror image of your right hand is kind of your other hand. And again, although you can pull the mirror image out, there's no way to rotate that in such a way that they fit perfectly on top of each other, again, in sort of the right orientation. And that's why a lot of times, sometimes these isomers are very hard for people to visualize, because you're like, well, if I just kind of turn it that way, it looks like it should fit. And again, a lot of times when we look at molecules, we sort of see it in kind of two dimension, kind of flat, if you will. But we have to remember, just like we learned with, say, Lewis structures and stuff like that, right? Things based on their bonds do have different bond angles, and that allows certain molecules, right, to kind of go forward, other ones go backwards. And as you rotate those things, you may end up with something sort of in the right location, but it might be pointing sort of the wrong way and stuff like that. So sometimes it gets a little bit difficult to sometimes mentally sort of try to decide, hey, what is going on in terms of these guys. So here we have isomer 1 and isomer 2. They are mirror images. The image of 1 is identical to 2 and cannot be superimposed. That is, there's no way that number 1 can be turned in space so that it is the same as number 2. And the main difference is, if you sort of look at it, if we do sort of our reflection here, again, the problem is we're going to have this guy reflecting here. This guy is going to reflect back, and this guy is going to reflect in. And what we end up getting based on that reflection is a very slight difference in sort of the connectivity. And it happens right here. So I won't draw too much to make it really bad. But you can see there's actually a connection that happens in our mirror image that's there, that is not in our original one, which means as we keep rotating this sort of guy around, we're always going to have that bond in sort of the wrong location. So because of how it reflects, this guy reflects, this guy sort of reflects backwards, and we get this reflection that occurs. We get this additional sort of connectivity that we don't have in the original one, that's not going to allow it to be rotated in any direction, where it will basically superimpose sort of correctly on each other. And here, though, if we look at A is the trans isomer, and his mirror image are identical and superimposable. So again, if we were to just kind of do that, we have this guy, which would reflect here. We have this guy, which would reflect back here, and same thing on the other side. And when we do pull that out, we actually do get something that looks identical to it, because again, we're going to get this sort of reflection. We're going to get this sort of reflection, and it's going to create the same sort of bond that's going to happen here. Again, when we look at this cis one, though, we do run into trouble. We're going to get that different connectivity as we get the reflection back. And again, you can kind of see that different sort of bond that develops here in our mirror image from the bottom guy to the back corner. And in our original substance, it actually only bonds to like here. So we don't have that extra bond that's happening. And thus we get that bond I was just talking about that's not going to allow it to superimpose correctly on each other. And that's what I was saying earlier. Sometimes these things are very hard for a lot of people, myself included, to sort of just visualize, they're not going to correctly look right. Again, just quickly look at it, and you may be thinking it kind of looks the same. I think, it should definitely kind of fit. But again, it's these slight little differences, like I'm showing here, that develops when you kind of just put it up against the mirror and you kind of draw the reflection that basically occurs. You get these sort of different connectivities that occur. So when we talk about enantiomers, they are basically two molecules that are mirror images of each other, and they are non-superimposable. So that means that they are chiral, right? Because they are non-superimposable, and they are referred to as enantiomers. And again, sometimes a lot of biomolecules are chiral. And again, sometimes one isomer is more effective than another. Again, there is some differences that's going to occur in some of the properties based on sort of the connectivity that we sort of get. And we'll have some differences. Any questions on sort of isomers there? All right. So what we're going to then talk about is sort of what happens in a complex ion in terms of bonding electrons and sort of, what is going on. And some of it is going to be sort of related a little bit to some of like the Lewis structure type geometries that you learned and sort of how they tie together. So the formation of hybrid orbitals to share electron pairs, if you remember, those are things like sp, sp2, sp3, sp3d, sp3d2. Those are where we get basically atomic orbitals, which are s's, p's, d's, that basically hybridize, and they hybridize to form these hybrid orbitals, which create guys that have the same shape. They also create orbitals that are in the same energy and allows for sort of better bonding and stuff like that. So we do see a little bit of that in terms of sort of our complex ions and sort of what develops in terms of their geometry. It is sort of relatable to the Vesper model, but not like perfect. We oftentimes do think of these interactions more like a Lewis acid and base, right? Which is why we call our ligands Lewis bases. Again, in sort of the accepting and donating of our electron pairs. And this is going to happen in most cases with our complex ions with our d electrons. And that's because, again, a lot of them are transition metals, and that is the part of the periodic table where we have transition metals is the d block. So it's really those d electrons sort of from the metal that are sort of involved in the bonding that occurs. Now, here you can see, for example, this guy has a coordination number of 6. Sort of an easier way to sort of think about it again is, if you remember, coordination number 6 is sort of our octahedral or 6 electron pairs. We think about just regular Vesper is octahedral arrangement, and that is sp3d2. By the way, if you just count this is kind of the electron pairs. There's 1 s, 3 p's is 4, 2 d's is 6. Yeah, so that's sort of the easy way in terms of hybridization. You count electron pairs and just basically go, there's an s, p, d, right? So if it has 2 electron pairs, it's an sp, right? If it has 3 electron pairs, sp2, right? 4 electron pairs, s, p1, p2, p3, right? So that's the way you could sort of figure out hybridization if you've forgotten how to do that. But here with our coordination number 6, again, that's one way you can kind of think of it. 6 is like octahedral. That should have that sort of hybridization happening. Here are other common hybridization that's occurring. And here, again, if we just kind of look, we got 1, 2, 3, 4. This is a coordination number of 4. And again, our coordination number of 4 going to be sp3, right? This is also a coordination number here of 4. But this is kind of, if you again want to sort of use the analogy, sort of relatable to your expanded octet. So this is where we have our sort of 6 electron pairs and 4 bonds, and that's our square planar geometry. And here is a coordination number of 2 happening, which again is our sp sort of arrangement. So based on the sort of coordination number, it sort of corresponds to some different sort of structure, geometry, and here's sort of the breakdown of sort of where we usually will end up with most of the stuff that we see. Again, if something has a coordination number of 2, again, you can think about it like VSEPR, 2 electron pairs is typically geometry or linear geometry. Something with a coordination number 4 is like 4 electron pairs is tetrahedral. Also square planar, again, for sort of your expanded octet is where we come across that guy. Coordination number of 6, again, sort of refers to kind of like 6 electron pairs, which is, again, very similar to octahedral in terms of its geometry. So when we talk about sort of bonding that's occurring and electrons and how they sort of make these bonds, there actually is sort of a change that occurs. So when we talk about electrons in the transition metal in a complex ion, we are talking about those d electrons, and those d electrons again are in the d subshell, which has 5 orbitals. As you hopefully know, right, only 2 electrons per orbital, right? And basically our transition metals on the periodic table start at the 3d level, right, as we talked about before. And these are the 5 different d orbitals and sort of their shapes. Now, when we have all of our d orbitals sort of on the same energy level, that occurs when there's really no ligand present. So in the absence of a ligand, all of the d orbitals will be exactly even, kind of like what I drew here. And what that means is when electrons go in, as you know, hopefully, they go in one at a time, right? So they go in one at a time upwards with a spin quantum number of a half plus a half. And then when it gets to the end, they come back and then they start kind of filling in, right? If need be. Now, what happens actually when we have a ligand present is that there's a splitting of these d orbitals. So when we get a ligand that's sort of present, we actually get sometimes some of these d orbitals to basically split. Perhaps we'll get 3 orbitals on lower in energy, 2 of them maybe being higher in energy. And that's really going to affect how the electrons go in. They may, go in one at a time and decide, well, we'll go up. Why not? They may actually go in one at a time and decide, no, I don't want to go up there. I'm just going to come back this way. And what's going to really determine sort of what happens with those electrons as they sort of fill is what is sometimes referred to as crystal field splitting. And crystal field splitting is the splitting that we see of those d orbitals in the metal, that instead of all 5 of the d orbitals in that subshell being perfectly equal in energy, we get this splitting where we get a couple of d orbitals that are actually higher in energy and some d orbitals that are lower in energy. And here what we're looking at is an example here of that splitting. And again, that crystal field splitting is what is referred to as the energy difference between sort of the lower set of d orbitals and the higher set of d orbitals. We could actually calculate the energy associated with that with an equation you've also probably saw last semester. E is equal to h times the frequency, h being Planck's constant, which is 6.63 times 10 to the minus 34 joules times seconds. That is actually not v, right? That's new. That is the velocity, not velocity. That is the frequency. Let me get that right. Frequency. And that, using that relationship, and also one that you also probably saw, c is equal to the wavelength times the frequency, c being our speed of light, which is 3 times 10 to the 8 meters per second. This is our wavelength in meters. And again, that's our frequency in reciprocal seconds, or hertz is what a frequency usually is in terms of units. Reciprocal seconds, which is the same as a hertz. And again, this is our wavelength, which is typically in meters. Putting both of those guys together, we actually can come up with a relationship to calculate this crystal field splitting, which is that energy difference. And we could calculate it as E is equal to H times the frequency, which would be the HC over the wavelength. So that relationship that you probably have seen previously as well is also something that we will see a little bit here in this chapter. Any questions on that? So what does it mean if we have a large crystal field splitting, we have a small crystal field splitting? It is going to affect how our electrons are basically populated in those d orbitals. So, for example, if I'm going to fill in my electrons here, go 1, go 2, go 3, and then perhaps the splitting is relatively on the small side, then we would expect these electrons to kind of feel like normal and then come back and start pairing off. Again, as I mentioned earlier, if it's sort of the opposite and we get sort of a larger splitting that's occurring, we would see a much difference in terms of how it's filled. It will come this way and feel like normal and go, nah, this is like too big here in terms of energy. I don't really feel like going that high. I'm just going to start filling this way first. And then if I need to, then I'll come up this way. And this is going to result in some different arrangement of our electrons in these sort of compounds. Remember that when we do have these electrons heading in opposite directions, this is what is sometimes referred to as paired spin, right? And by the way, when we put a electron in first into an orbital, it goes up with a spin quantum number of +1/2. The second electron goes in down with a spin quantum number of -1/2 when you do that. Now, that's different than when we put them in sort of one at a time. This is what is sometimes referred to as parallel spins, right? And a lot of times a very stable arrangement in normal electron configuration is where we get something like Hund's rule. We get basically maximizing the parallel spins, which is why they do go in sort of one at a time before they come back and sort of pair off. So as I mentioned before, we can excite an electron by shooting some energy at it. And that's basically the idea here of our absorbance. We do hit maximum absorbance here at a specific wavelength. And this is why we oftentimes will set our spectrometer to a specific wavelength that basically corresponds to where we see maximum absorbance. So again, this is the equation that we can use to do our crystal field splitting. And sometimes this is even just sort of abbreviated with the delta symbol without the E. And you'll sometimes see it just like this. So sort of the same idea here. By the way, when we do see sort of color in the visible part of the spectrum, right? The visible part of the electromagnetic spectrum, where Roy G. Biv is where we see colors. What we actually see is the complementary color to what is being absorbed. So, for example, if our solution looks red, we actually don't set the wavelength to red's wavelength. We actually set it to its complementary color. So what we actually see is sort of, again, the complementary color to what is being absorbed. So that's why we see sort of those different colors. And that's why if you ever wondered when you do experiment that involves, say, like a Spec 20 or, some type of spectrophotometry, we oftentimes will set the wavelength to a wavelength that doesn't necessarily correspond to the color of our solution. And it will oftentimes correspond to the complementary color to our solution. So looking at an example here, which I think was filled in for you. So we'll just kind of go through the calculation just to make sure everybody's on the same page. We have the absorbance maximum here for a complex ion. It occurs at 470 nanometers. What is the color of the complex, and what is the crystal field splitting? So we got a couple of different things happening here. First off, we'll start with what is the color. So if we think about sort of 470, 470 is the color at which it absorbs. So 470 would be, in this region. And that is the color of blue. Its complementary color, as we can see here from the color wheel, is orange. So to us, it will appear orange as it absorbs over here in the blue range. Just like if our solution looked red to us, we would set the spectrophotometer in the green section or wavelength. Again, that's where we'd probably find our maximum absorbance happening. Same idea if we had a nice purple color, we would set the absorbance to yellow and vice versa. So again, what the color appears to us in the visible part of the spectrum is its complementary color to the wavelength of light that is being absorbed. So that is the color. We could figure out the crystal field splitting by, again, using our E is equal to H times the frequency, which is HC over the wavelength. And since we only have the wavelength given to us, we would want to use sort of this relationship. Again, H is a constant, which is right here. That is the 6.63 times 10 to the minus 34. Again, joules times second. This is the speed of light. So again, that's H. That is C. Also a constant, so you always have that number. So we do need to do some adjustment here on our wavelength, and that is because, again, unit-wise, it's in nanometers. But in order for all the units to cancel out correctly, it needs to be in meters. So that's why we have 470 times 10 to the minus 9, 10 to the minus 9 meters in a nanometer. So that's where that conversion comes from. If we do all that, we get something like 4.23 times 10 to the minus 19 joules, and that is per atom, which is what we have here. So since we're looking for kilojoules per mole to go from atoms to mole, you probably know that that is our good friend Avogadro's number, right? So 6.022 times 10 to the 23. And that's why we have this part of the calculation here. That's going to give us 6.022 times 10 to the 23 atoms over moles. The atoms will cancel, going to leave us joules per mole divided by 1,000 gets us to kilojoules per mole. So the first part of calculation is pretty easy. It's just a plug and chug into here. Make sure, obviously, that you have the correct units. Second part is really just using Avogadro's number to convert it into per mole. We're basically multiplying by Avogadro's number. Any questions on that calculation, where we got any of those numbers from, or anything like that? So again, this is how we could calculate the crystal field splitting, which, just so we're all clear, that is the separation, the distance basically between the lower set of d orbitals and the higher set of d orbitals in a complex ion. So the question is, do I have to do this calculation to figure out, is that splitting large or is that splitting small? The answer is not necessarily. There is a way that you can determine whether or not you would anticipate the splitting to occur sort of high or low, or be big or small. And that is through the use of what is sometimes referred to as a spectrochemical series. And these are basically a series of ligands that basically gives you an idea as to sort of how the splitting of those d orbitals will look. And by the way, just so we're clear, the splitting that we're looking at here is what is referred to as the octahedral splitting for somebody that has a coordination number of 6. So this specific arrangement of these 3 d orbitals on the bottom, those 2 d orbitals up on top, kind of the squares up on top, the non-squares on the bottom, that is specifically with the way that the splitting occurs with somebody with a coordination number of 6. So on this side, on the right-hand side, where we have things like En, Cn, over here in this range, this is strong field ligands. So what does that mean? Well, strong field ligands means that this splitting is going to be relatively large, which means when we have something like that, we're going to end up with these electrons going, I'm going in, I'm going in, I'm going in. Whoa, that's a strong field. That is way too high to go up there. I'm just going to start to fill down first. And what we end up with in that particular case is obviously something where we get a lot more paired electrons. And we get a lot more paired electrons here in this situation. And that is what is referred to as a low spin complex. Electrons obviously have spins, but when you pair them off, they sort of cancel each other out. So we end up with not a lot of unpaired electrons. We end up with a lot of paired electrons, and we end up with this kind of low spin complex. And that is different than if we get somebody that's on the left-hand side as being part of our ligands. And our guys on the left-hand side is what is referred to as a weak field ligand, which means the separation between the lower d orbitals and the higher d orbitals is actually a smaller separation. And what that means is when it decides, hey, that's not too bad, we'll just go in, go in, go in. It's kind of small. We'll just fill it in like this. And you can see in this sort of situation, you're probably going to end up with a lot more unpaired electrons. Unpaired electrons means paramagnetic, right? A lot of unpaired electrons happening. And that also results in what is sometimes referred to as a high spin complex. So high spin complex, you end up with more unpaired electrons. Low spin complex, you end up with more paired electrons. So your question may be like, what about our guys kind of in the middle? Well, there's a couple of different things that can sometimes happen with our guys in the middle. First off, they may just straight out tell you in a problem, do this for the low spin situation or do this for the high spin situation. And if it was the low spin situation, that means that you would assume that the splitting is going to be small, and that's how you would distribute the electrons that are in the d orbitals. If it was told you to do sort of the low spin, that means that you expect that difference to be to be large, and you would pretty much pair up your guys on the lower d orbitals first. And there's other cases where it may not make a difference. So what I mean by that is, if you did it, for example, high spin, and then you did the same sort of guy for low spin, you may actually end up with the same sort of arrangement. And usually in these questions, they oftentimes will ask you, how many unpaired electrons would you expect to find? And again, you can sometimes have a situation where, depending on the ligands, regardless of sort of which way you do it, sort of high spin, low spin, weak field, strong field, you oftentimes can get sort of the same outcome. So if you come across a problem where they really don't specify something, it's maybe not really clear as to, is that ligand sort of in the middle-ish? Is it weak field, strong field? It may actually be a case where it will not make a difference at all which way you do it, and you'll end up with sort of the same situation. So that definitely does occur. So again, just so we're clear, what we're talking about here is distributing the d electrons in the transition metal that is in the center of our complex ion. So we're talking about how those electrons are distributed in that case. Any questions on that there? So let's take a look at sort of two examples here, and just to kind of see, how we got to each of these. So for example, here, if we look at our first complex ion, which is this guy here. So we have basically this situation. We have Fe, F6, and it is a -3. So the first thing you probably want to figure out is sort of what is the oxidation state of the metal here in our complex ion. We know that F is -1, and there's 6 of them, which means it's -6. That means the important part here is the charge really on the iron is going to be +3. So if we look at iron's configuration with no charge, that's not what I want to do. I want to do this way. So if we look at iron, no charge, it is 26 there on the periodic table. And if we write the configuration, it is going to be argon 4s2 and 3d6. Now, what we're dealing with in this complex ion is an iron that has a +3 charge. So as we talked about at the beginning of this chapter, when transition metals lose electrons, they lose the S's first. So this iron is going to lose the 2 electrons here, and then it's going to lose the 3rd electron out of there. And that's going to give us an iron that has a +3 charge, having a configuration of argon 3d5. And it is those 3d5 electrons that we are talking about distributing here. Any questions with that? So when we're talking about sort of how these electrons are distributed, the iron, which is in the center of this complex ion, has a +3 charge, which means it basically has 5d electrons available to it. Any questions up to that point? So if we look at our spectrochemical series, we see F is sort of on this side-ish. So we'll go with it as being a weak field. And what that means is we will expect a small separation between our lower d orbitals and our higher d orbitals. By the way, this guy obviously has a coordination number of 6. So we're going to see this octahedral splitting. And we would put our first electron in here, as you can see. Our second electron would go in here. Third electron would go into here. And because the splitting is small, this crystal field splitting here is relatively small, our next electron would feel kind of like normal in the top one and then the next one here. So what we end up with at this point is 5 unpaired electrons in this particular complex. And that is definitely what is referred to as being a high spin complex. Again, you have a lot of unpaired electrons in this particular case. Any questions on that one there? Now, if we take the same guy that's over here, we have FeCN6, and we have a -3 on that guy, I think, as well. So same idea, Cn minus is -1. There's 6 of them, it's -6. Again, here we have a +3 for our iron in this particular case. So we're going to be starting with our same 5 electrons. The difference, though, is we have Cn minus as our ligand. And Cn minus is definitely strong filled, which means that this separation here is going to be large, as opposed to over here, which is going to be small. And what's going to happen when we go to distribute those 5 electrons is first one is going to go up, second one is going to go up, third one is going to go up. Then coming back, we're going to pair at this point down for the fourth and down for the fifth. That's because when it gets to the fourth electron, it's like this is too big of a difference. I rather go on the lower ones. What that's going to give us is actually only one unpaired electron. And this is what is sometimes referred to as a low spin complex. Again, it only has basically one unpaired electron. Question on that there. So why don't you try one just to see here? Why don't we try, let's do, actually here, I'll flip this page real quick. Why don't you do this guy? And figure out, what is draw the splitting with the arrows and figure out how many unpaired electrons you have. So take a minute or two there and come up with it. Cobalt, by the way, is 27 on the periodic table. All right, take a minute or so and then we'll talk about it. What we got going, we'll first start with obviously what is the charge on cobalt. So Na3 is 0 and the overall guy is +3. That means cobalt really has a +3 charge. That also means that if we did cobalt with no charge, it would be argon 4s2, 3d7, I believe in this case. And in this case, it has a +3 charge, which means it's going to lose these guys here, and it is going to lose that guy there. That means our cobalt with a +3 charge would be argon 3d6. So we really have our 6 electrons to distribute. And in this case, we would have a coordination number of 6, which means we would get the 3 d orbitals on the bottom, the 2 on top. Again, this being our x squared, y squared, and our z squared, and our xy, and our yz, and our xz happening here. So we need to decide maybe NH3. And again, NH3 might be one of those ones that are kind of like, on that bridge and stuff like that of is it strong or weak? And we'll go with it being strong in this case. And again, you oftentimes will have maybe some direction as to, how to do it. They may say do it as strong or do it as weak and do it as low or high spin. So we'll go for the first one here as strong. And what that means is, where did I go there? There it is. So if we do this as strong field, we would distribute our 6 electrons as follows: 1, 2, 3. Because this is strong field, we would then go back and put them on the lower ones, and we would actually end up with no unpaired electrons in this case. And this definitely would be a low spin complex. Now, if you did it the opposite way, and maybe they wanted you to do it as high spin, although I kind of drew it backwards, I think, we would go, if we did weak filled, it would be 1, 2, 3. Then it wouldn't be so bad. 4, 5, and 6. And this would result in 4 unpaired electrons, which would be high spin. Probably going to go this way with it because it is kind of closer, probably the strong field. But again, some of those ones in the middle, you will get some direction, and that's what both of them would look like. Any questions on how to distribute that? And that's what we sort of see here on the screen on the left. There on the left, we have our high spin, which means we basically have weak field. So the separation here is relatively small in all these. And as you can see here, it results in a lot of unpaired electrons, which again is what is referred to as being high spin. And on the right is our more strong field, where we have obviously a greater separation, better than I drew on the right there. And because of that greater separation, we're going to get a lot more pairing off happening in the lower guys. and that's going to result in a more low spin complex where we have, not as much happening in terms of single or unpaired electrons. Any questions on that? All right. So what we've been talking about is seen here is specific for our coordination number 6, or octahedral. When we get to a coordination number of 4, that is tetrahedral, in terms of its geometry, we actually get this splitting, which is opposite. We actually get those 3 that were on the bottom in octahedral go to the top, and those guys that were on the top in octahedral actually go to the bottom here. Works the same way. Again, we're going to fill these guys here first and then decide, should you go up? Should you just stay down based on how big that crystal field splitting is? So for coordination number 4 that has tetrahedral geometry, this is the splitting. It's basically opposite of the octahedral. Works the same way. Again, you would want to figure out how many d electrons you have in the transition metal with its charge and distribute them accordingly based on the ligand that's attached to it. In addition, for a coordination number of 4, there's also square planar. And you can see a much different sort of splitting pattern that occurs here. Again, you would fill in lowest to highest, depending on sort of the splitting that's occurring. Are these splitting parts large or small? So for us, we're going to not worry about this one. So you don't have to worry about this splitting. You do have to worry about this one. You're responsible for knowing how to tetrahedral the coordination number 4 and draw the arrows in and the splitting. And then obviously our octahedral guy that we saw here, you need to know the octahedral splitting. So in terms of crystal field splitting, those are the ones you'll be responsible for. Octahedral, coordination number 6, the splitting pattern, and then also the tetrahedral splitting pattern, which again, they're pretty much similar. They're just opposites of each other. Any questions on that there? Okay, that should wrap up this chapter. So let's talk about a couple of things that's happening. We have the exam coming up in about a half hour or so. So about 11:30 it will open. Again, you're expected to take it obviously when it opens in that period. You will have problems obviously like normal that you need to show the work. So you need to make sure you show all the work, the units, the setup, all that type of stuff. That stuff does need to be submitted immediately after the exam or you will not get credit. So make sure you don't forget to do that immediately afterwards. Make sure that obviously your online answer matches your work answer. Everything you need should be there. There's a bunch of tables on this one. So there's also some PDF files of those tables just in case you can't see the picture and stuff like that. So you may have to open some of those tables in PDF form. So they're in there in picture form and also PDF form. So you could be able to find that. Obviously a periodic table like normal as